everyone. Today our topic is convex optimization, and our team member is Jiliang Wang and Yue Gong. So today we will introduce the convex optimization from four paths. The first is the introduction, and the second is convex sets, and the third one is convex functions, and the last is convection optimization problems. In this part, we will just do some brief introduction about the convex optimization. So at first, about the introduction, we will talk about the history at first. The theory of convex optimization has been studied more than 100 years old, but recently years it just developed because until 1980s the interim point methods has been found slowed about the linear programming problems, and it can also be found to solve the convex optimization problem. So the convex optimization developed. And before 1990s, convex optimization mostly used in some operations research and just a few in engineers. But after 1990s, there are many new applications in engineers, just like control, synchronous process, and so on. And some new problems class, just like semi-definite problems, also can be solved by this method. And for the second part of introduction, we will talk about the objectives and topics about this presentation. We just do some brief introduction about the convexes, convex functions, and the convex optimization problems, and we use some simple examples and to help to understand easily about the convex optimization. This is some basic knowledge we need to know at first. The first is the mathematical optimization problems. We need to minimize the f0x and subject to fix less and equal to bi. For these functions, we need to know x is equal to x1 to xn. This is the optimization variables, and f0 is Rtn to R. This is the objective functions, and fi, this should be fi is the constraint functions. For the optimal solution x star, it needs to have the smallest value of fn fi among all vectors and satisfy the constraints. And the next knowledge is that the function of a convex optimization problem, we need to minimize f0x and subject to fix less and equal to bi. And for the objective and constraint functions, it is convex, so we can also write the function just like the fix plus beta y less and equal to alpha xix plus beta fiy. And in this point, alpha plus beta need to equal to 1, and they both great and equal to 0. This is the second part of a convex optimization. It is the convex set. First, we need to know when x1 not equal to x2, there are 2 points in this. The form we can write as x equal to theta x1 plus 1 minus theta cross x2. And we talk about the affine and convex sets. First, what is the affine set? A set S in at N is affine if a line through any 2 distinct points in S lies in S, which for any x1 and x2 in R and theta also in R, we have these functions. This is the graph of the affine set. We can say this is when theta equal to 1, we have x1, and when theta equals to 2, we have x2. For the convex set, a theta is convex if the line segment between any 2 points in S. So what is the line segment? Between x1 and x2 or points, we have this function, and the convex set is theta x1 plus 1 minus theta cross x2 in S. For these 3 graphs, the first is convex because it is boundary all points in the graph, and this is not convex because for the point between this are not in the set S, and this is also this square is not all boundary because we can see this point is empty. And for the columns, it called the columns is for every x in S and theta greater and equal to 0. So we can get theta x in S. So we call theta s is a convex corner if it is convex and a corner which for any x1, x2 in S, theta 1, theta 2 greater and equal to 0. We have these functions. There is a conic combination of x1, x2. It is for any point of the form x equal to theta 1 cross x1 plus theta 2 cross x2. So this is the form, and we can also get the example of this graph of the corners. We also talk about some important examples. We mentioned some simple examples in our report. So in the presentation, we just talk about some important examples. The first is the hyperplane and half space. What is hyperplane? It is the set of the form of this form, and the hyperplane divided into half spaces. So the half spaces is the set of. So we need to attention. This is equal and this is less and equal. This graph is the hyperplane, and this graph is the half space. We can know that it is divided. And the hyperplanes are often and convex, but the half space are just only convex. There are also some important examples, other examples, just like ellipsoid, normal, and so on. But we write the details in the report, and we will don't show for this presentation. And for the third one is convex function. Convex function, the first is the definition. Just as it said, it is f of the theta x plus y minus theta cross y. It should be less than equal to theta fx plus y minus theta cross fy. For the extended value extension, if we want to extend a convex function, we need to define this value to be infinity outside of its domain. So if f is convex, we can just define its extended value extension f for this. So it's just separate in two parts. The first, if x is in the domain f, it should be fx, and if it is not, it will be infinity. And for the first order conditions, if f is differentiable, if the domain f is open and the gradient just like this existed in x in domain f, and the first order condition is the differentiable f with the convex domain is convex if if for these functions, and the first order approximation of f is global underestimate. So there is another part. My team member Jiliang will introduce the rest.
Okay, let's take a look at the optimization problems. This is a standard form of optimization problems. Here, this for Fi and Hi. Fi is the inequality constraints, and Hi are the equality constraints. And in addition, there are some implicit constraints, such as that x should satisfy that it should lie in the domain of Fi and Hi. Next, I would like to talk about the convex optimization problems. This is the standard form of this problem, and here we need to pay attention that Fix for this constraint it is convex, and for this equality constraint it is affine. For convex optimization problems, there are some special properties. The first one is that there is no local minimum, which means any local optimum is necessarily a global one. And its another property is the algorithms are easy to initialize by using duality theory. And the third one is efficient numerical solution methods that can handle very large problems. This is a quasi-convex optimization. The difference between convex optimization and quasi-convex one is that the objective function f0 is quasi-convex, and for this optimization problem, there can have one local optima for this problem. Next, I would like to talk about some canonical optimization problems. including the first one, the linear program, the second one, the quadratically constrained quadratic program. The third one is second-order cone programming. The fourth one is semi-definite program. The linear program has this form. So it is a convex problem with affine objective and constraint functions, and the feasible set is a polyhedron, which is shown here. And for the QCQP program, it has this form. So as we can see, the objective and constraint are convex quadratic. You can see here. And for the SOCP program, it has this standard form. When ni is equal to 0, so SOCP reduces to an LP program. If Ci is equal to 0, and it will reduce to a QCQP program. So we can see that SOCP is more general than LP and QCQP. The last one is a semi-definite program. It has this standard form, and as we can see, the inequality constraint is a linear matrix inequality. This is the difference. So this is our reference, and that's all. Thanks for your watching. 回去剪。